Welcome friends to today's session of live lectures. For today's session we have with us Dr. Neeti Bhutani. Dr. Bhutani is Assistant Professor in Hindu College under Delhi University. She has got her doctorate from University of Maryland, which is in US, and she has several news articles and policy reports under her credit. Friends, today's topic of discussion falls under the series of mathematical methods for economics, and the topic is set theory. Let's welcome Dr. Bhutani and let's carry on with the topic. We welcome you, Dr. Bhutani, and please guide us on to the set theory.
Thank you very much, Disha. Hi everyone, I welcome you to yet another lecture of mathematical methods for economics. The lecture today will be entirely devoted to a discussion of set theory. In fact, I had started talking a little bit about set theory in my previous lecture. So today we'll build on that. We will introduce some new concepts and also work our way through some problems. But even before that, let me do a quick recap of the basics that I had covered in my previous lecture. Starting with the definition, we defined a set as a collection. It is a collection of well-defined objects which are known as the members or the elements of the set. Now these objects or the elements, they are typically such that there is some common property that binds these elements together, by virtue of which they are members of the set. So please take a look at this slide to see some of the examples of sets that we discussed in the previous lecture. We started by talking about the set L, which we described as the set of all Indian authors whose books are stocked in your college library. Let us suppose that your college library keeps the books by Amish, Anita Desai, Amitabh Bagchi and Manju Kapoor. Then these would be the names that would figure in the set L. Similarly, we defined the set A as one that has all the letters of the English alphabet. But you could also have a set G where really there is no common property that links up the elements together. So if you look at this set G, it has as its elements A, B, C, 1 and 2. And really there's nothing in common that links up all of these elements together. But the point here is that if you do have some common property by which you can bind these elements together, it might be a good idea to actually write your set in terms of the common property, because especially in cases where you have an infinite set with an infinite number of elements, or it's just too much of a hassle to write down so many elements, the property gives you a compact way of representing the set. So for example, the set A, where we wrote that the set A is the set consisting of the letters of the English alphabet, we can simply write the set A, if you follow the cursor here, the set A is a set of all elements X such that X is a letter of the English alphabet. Similarly, we could define the set of positive integers I plus, which is the set of all elements Z, such that Z is a positive integer. And here you'll have the elements as 1, 2, 3, 4 going on till infinity, but you don't have to list out the elements. Finally, we, as the last example, we talked about the set T, where we defined it as a set of all elements X, such that X lies in the closed interval from 0 to 3. Here we are including the endpoints 0 and 3. Now, we can distinguish between two kinds of sets. We can talk about a finite set, or we could have an infinite set. A finite set is one that has a finite number of elements, as the name suggests. So for example, if you look at the sets defined by L, A and G here, if you follow my cursor, these are examples of finite sets where you can where you're absolutely clear about the number of elements which are there in this set. So if we represent, let's introduce some notation. If you represent the number of elements in the set S by n of S, this notation here, then n of L would be 4, n of A would be 26. We have 26 letters of the English alphabet, and the number of elements in G, n of G, would be 5. And in this sense, these sets are examples of finite sets. Then you could also have an infinite set, and an infinite set is one that contains an infinite number of elements, an immeasurably large number of elements which you can't count as such. So if you look at our examples, in our examples the set I plus would be categorized as an infinite set. Here you have all the positive integers, and this is clearly it's a set where you have an infinite number of elements. Then similarly the set T is also an example of an infinite set. And finally, last time I talked to you about the budget set, which diagrammatically looks like the shaded region in blue here, and this also is an example of an infinite set. The budget set here is being described as the set B, which is a set of all consumption bundles such that all these inequalities are satisfied. And how do we define a consumption bundle? Let us suppose you have a world with only 2 goods, and in that world your consumption bundle is defined by x comma y, where x is a number of units of good x that you buy, and y is a number of units of good y that you buy. In our example, we took x as a number of Maggi packets that you buy and y as a number of t-shirts that you buy. So in this sense, x comma y is your consumption bundle. Let us suppose your price of x is 20 rupees per unit and the price of y is 200 rupees per unit. Then what the budget set says is that your spending, which is the value of your spending, which is given by 20x plus 200y, that value of your spending cannot exceed 1000, which here is your pocket money. So the spending 20x plus 200y always has to be less than or equal to 1000. Then the other two inequalities simply state that x and y can't be negative. It's simply saying that you can't consume negative quantities of the 2 goods. So diagrammatically, the budget set is the area which is enclosed by the axes and what is known as a budget line. The budget line, if you follow the movement of my cursor here, this is a budget line which gives us all the feasible consumption bundles that you can buy if you fully exhaust your income. So the equation of the budget line would be 20x plus 200y is equal to 1000. If you fully exhaust your income, you'll be on the budget line, but if you are spending less than your income, you'll be somewhere in within the set shaded in blue. So this clearly is an example of an infinite set. Right. So now we're going to categorize these infinite sets a little further. Our 2 examples of infinite sets that we considered were S and T. So actually S is, I've modified it a little bit. So if you consider the set S here is a set of all elements Z such that Z is a positive even integer. In other words, here the set S will have as its elements the integers 2, 4, 6, 8 and so on. You're taking all positive even integers. And then consider the set T, which is the closed interval from 0 to 3. Now both of these are infinite sets. The question here is there any feature that if you stare at these 2 sets hard enough, do you see any feature by which you could distinguish, you could make a difference, you could tell some difference between the sets S and T? And the answer here is yes. So listen to me carefully here. If you look at the set S has as its elements the positive even integers 2, 4, 6, 8 and so on. Now what I can do with this set is the following. What I can do here is I can relabel the elements of this set. So if you see these arrows here, I can relabel the element 2 as 1 I can relabel 4 as 2, I can relabel 6 as 3, 8 as 4, and so on. The idea being that now I can start counting my elements. In other words, here 2 is my first element, 4 is my second element, 6 is the third element, 8 is the fourth element, and so on. So the idea here is that this is a set where I can count the elements. Obviously, because this is an infinite set, I can't count all the elements, I can't count the total, but the idea is that this is a countable set in the sense that I can now establish a one-to-one correspondence between the elements of the set and the set of natural numbers. So if you look at the way I have written down things here, the set of natural numbers is 1, 2, 3, 4 and so on. So now the natural number 1 stands for the element 2, the natural number 2 stands for the element 4, the natural number 3 stands for the element 6, and so on. So this way we have established a one-to-one correspondence. There's a linkage now, a one-to-one linkage between the elements of the set and the set of natural numbers, and such a set is known as a countable set or a denumerable set. This is an important definition, so please pay attention. So we have just described what is a countable or a denumerable set. The question is, can I now do this similar kind of exercise, this counting exercise for the set T? Now the idea behind a countable set is that I can count the elements. I can look at, if you just back up for a second, my 2 was my first element, 4 was my second element, and so on, which also means that if I identify any 2 particular elements in this set S, for example, let's take the elements 2 and let's take the element, let's say 10, then I can actually count the number of elements between those 2 members. So here I'll have 4, 6 and 8 lying between 2 and 10. So I can say there are 3 elements lying between 2 and 10. So now our question was, can I do this similar exercise for the set T? Let us identify in set T 2 elements. So let's take for example 0, which is an element of the set T, and let's take for example 0.5. The question now is, can I count the number of elements between 0 and 0.5? Here the answer is no. We can't even make a start because again there will be an infinite number of elements between 0 and 0.5. So this kind of a set T is known as an uncountable or a non-denumerable set. Similarly, the budget set is also an uncountable or a non-denumerable set. Here we cannot establish a one-to-one correspondence between the elements of the set and the set of natural numbers. So we can't identify a particular number as a first element, the next number as a second element, and so on. And finally, needless to say, finite sets are always countable because finite sets have a finite number of elements, so these would always be countable. Right. Let us now talk about the equality of sets. 2 sets A and B are said to be equal if every element of A is also an element of B, and similarly every element of B is also an element of A. For example, let us suppose our set A is defined by the elements A, B and C, and the set B is defined by the elements B, A and C. So here we see that both the sets have the same elements, even though the ordering of the elements is not the same in both sets, but that does not matter. The point is that every element of A is in B and every element of B is in A, and therefore A is equal to B. The next idea that I would like to introduce is the idea of a subset. So this is something you must have already done in school, but let's revisit this in any case just to make sure that we are on the same page. Let us suppose that we have 2 sets A and B. Now if it is true that every element of A is also an element of B, every element of A is also an element of the set B, then we say that A is a subset of B. In terms of the notation that we use for a subset is here on the slide where my cursor is pointing. So this is a notation for A being a subset of B. And when we say A is a subset of B, mathematically it is equivalent to saying that if there is an element X that belongs to the set A, then this also implies that the element X has to belong to B, because A is a subset of B. And note here, this epsilon symbol is a symbol for belongs to, and if I put, this is for the future lecture, so if I put a slash on the epsilon symbol, then it means does not belong to. Coming back to the discussion of subsets, let's take an example. Let us suppose the set B is defined by the elements 1, 3 and 5. Then the subsets of this set B would be, first of all, the null set. The null set is a set that has no elements. So because it has no elements, this can be conceived of as this is actually a subset of every set that can be conceived. Then the other subsets of the set B would be the sets A2 consisting of 1, A3 consisting of the number 3, A4 consisting of the number 5, then A5, A6, A7, and finally A8, which you can see is nothing but the set B itself. And in this context, we can define what is known as the proper subset. What is known as a proper subset? So if we have a situation where A is a subset of B, and at the same time the two sets are not equal, at the same time A is not equal to B, then we say that A is a proper subset of B. So if you see the notation, we will write it, we'll put the subset sign but without the equal to sign, because here we are not having A equal to B. And in terms of the example that we just did, all the sets except for A8 will be proper subsets. A8, if you notice, is nothing but the set B itself. So this will not be a proper subset, but the rest of the sets will all be proper subsets in the sense that there is at least one element of B which is not present in these sets. Also, an interesting piece of information which might be useful to you is that the total number of subsets that you can have is given by 2 to the power n for an arbitrary finite set. In this example that we just did, we had 3 elements. So you can see we have 2 to the power 3, 8 subsets. Similarly, if our set had, let's say, 5 elements, then we would have 2 to the power 5, which is 32 subsets. Now, moving on to the next example for understanding subsets, let us define the set A as the set of all inferior goods. An inferior good is one whose consumption falls when income increases. Typically, for a normal good, your consumption would go up when income increases, but an inferior good is one for which consumption falls when income increases. And an example of this is, for example, bus rides. So typically, when your income goes up, you are better off. You would tend to switch to your car or some better mode of transport. So let's define A as the set of all inferior goods, and let's define B as a set of all Giffen goods. Giffen goods, I can't get into all the details here, but you would already know this if you've done economics. But if you haven't done economics, Giffen goods are a type of inferior goods, but the difference here is that instead of getting the regular downward sloping demand curve, here you have a situation where the demand curve becomes upward sloping, in the sense that if the price of a good goes up, then other things remaining equal, the quantity demanded of that good will also go up. So here we have a situation where the set B will be a subset of the set A. Then similarly, you can think of all rational numbers as one set and all real numbers on the number line as another, and you can think of the set of rational numbers as a subset of the set of real numbers. Now, we can also show subsets through a Venn diagram. A Venn diagram is nothing but a diagrammatic representation of sets where you show sets through a closed region in a plane. So here we have two sets, P equal to 1, 2 and 3, and the set Q, which has as its elements the numbers 1 through 6. So clearly P is a subset of Q, and diagrammatically I have represented my sets in terms of these circles. So because P is a subset of Q, I will show P totally enclosed within Q. So this is the Venn diagram for a subset. Now we will move on to some set operations. The first set operation, which you must already be familiar with, is A intersection B. The intersection of two sets A and B is denoted by an inverted U. This is the notation for A intersection B. And just as the word intersection suggests, here we are looking for the common elements between the two sets A and B. In terms of the Venn diagram, you can see that if you look here, the common elements, the region where the two sets overlap, that corresponds to A intersection B, and you can see here this region is shaded in blue on the slide. Mathematically, A intersection B stands for all the elements X such that X belongs to both A and B. I have put and in italics here to indicate that this is a key word. So whenever we talk of intersection, the key word is and. As an example, let's consider a set A, which is equal to 0, 1, 2 and 3, and a set B, which is equal to 2, 3, 4. Then in this case, the intersection of A and B is going to be 2, 3, because you can see here 2, 3 are the only elements which both these sets have in common. The next set operation is the union of A and B. Here we can think of the union as a situation where we are bringing the two sets together. So in terms of the Venn diagram, you'll see the union as the entire shaded area that spans the two sets. The notation for union is, the union operation is the capital U letter that we have in the English alphabet, and mathematically A union B is given by the set of all elements X such that X belongs to A or X belongs to B. Please note here that the key word here is or. Whenever we talk of the union of two sets, it means that we are talking of elements that belong to either A or B or both. And in that sense, we get the entire shaded area here. We are talking of elements belonging to just A or the overlap between A and B, if you follow my cursor, or just B. In terms of the example that we were doing, A union B would be simply all the elements of A, 0, 1, 2 and 3. And then we will add to that the element 4, because there's no point in writing the elements 2 and 3 again from B. So the only element that we have to now take into account is 4. So A union B would be 0, 1, 2, 3 and 4. Now the third operation is A minus B, where we look at all the elements which are present in A but not in B. The notation for this is A backslash B. So in terms of the Venn diagram, it means that you take the set A and remove from this set all the elements that correspond to B, which means that any element in this intersection here, if you see my cursor, this intersection area would have to be excluded, and therefore what we'll be left with for A minus B is just this shaded area. And mathematically, if you write things, this is nothing but A minus A intersection B. So A minus B is nothing but the elements, the set of all elements X, such that X belongs to A and at the same time X does not belong to B. And if you look at the example here, in our example, the set A is 0, 1, 2, 3 and the set B is 2, 3, 4. Then in this example, A minus B would be what? You'll take all the elements of A, 0, 1, 2, 3 and remove from this set whichever elements are also in B. So you have to remove from this set the elements corresponding to A intersection B, which is 2, 3. So your A minus B would be 0, 1. Similarly, when I look at B minus A means I'll take the set B and remove from this set all the elements that are from A. And what are the elements that are from A but also present in B? These would again be the elements in A intersection B. So from here I'll have to remove 2, 3 and I'll be left with the element 4. So B minus A is 4. Now note here that if we have two sets A and B which are mutually exclusive or disjoint, by mutually exclusive or disjoint I mean sets that have no elements in common. So in terms of a Venn diagram, I'll be just showing two sets which have no overlap between them. And for two sets that are mutually exclusive, which have no elements in common, the intersection between the two sets is nothing but the null set. The null set which has no elements, it is represented by phi or just in terms of braces. And now the number of elements in A union B for these mutually exclusive sets would be simply given by the number of elements in A plus the number of elements in B. Right. So we have to do some more set operations, but we have come to the end of this first segment. We will now take a short break. So we'll come back to this after I get back. Over to you, Disha.
Thank you so much, Dr. Bhutani, and thank you to all of you for joining us for this session. Friends, we want to inform you if you have any questions regarding this session, you may call us in last 10 minutes of this session on our toll-free number, which is 1800-110-430, and after that we'll meet you after a short break. Welcome back, friends. Before going on to the break, we were discussing about set theory, which falls under the mathematical methods for economics. We have with us Dr. Neeti Bhutani, and we'll continue with the topic. Before we'll start with the topic, I would like to inform you, if you have any question regarding this session, you may call us on our toll-free number, which is 1800-110-430. 110430. Let's welcome Dr. Bhutani. We'll welcome you, Dr. Bhutani, and let's start with the topic.
Thank you, Disha, and welcome back, everyone. So we were talking about set operations before the break. Let's continue with that and practice some of these set operations through some examples. Let us consider this example where the set A is the open interval from 0 to 2, and the set B is the set of all elements x such that x is greater than 1 but also less than or equal to 3. So here in this situation, the union of the two sets A and B would be nothing but the operation where we bring the two sets together. So we have to take the union of 0 to 2 and 1 to 3, which is nothing but the interval from 0 to 3, but we will not include the endpoint 0 because that's not included in either one of these sets. Then the intersection of the two sets A and B would be the overlap, and as you can see here, between 0 to 2 interval and 1 to 3, the overlap would be falling in the interval, in the open interval 1 to 2. Third, suppose we have to calculate A minus B. A minus B means we take the set A and remove from this set all the elements that are present in B. So here the elements that are also present in B would be the elements from 1 to 2. So in that sense, we'll get A minus B as a set of all elements x such that x lies between 0 and 1, with 1 included on the right hand side. Because 1 is not included in the set B, we can include it here. And finally, we have B minus A, which is a set of elements x such that x will belong to B but not A. So not A would mean that we'll have to remove the elements 1 to 2 from the set B, and therefore B minus A would be the set of all elements x such that x lies between 2 and 3. Now, for some interesting operations, these are questions that my students typically ask me, so I thought I'll include them here as well. The question here is, if A intersection B is equal to A intersection C, does this imply that B is also equal to C? And the answer here is, actually I should write not necessarily here instead of no. So to see this, let's take an example. Let's suppose A is 1, 2 and 3, and the set B is defined by the elements 2, 4. The set C is defined by the elements 2, 5. Here if you see, A intersection B is the element 2 and A intersection C is also 2. But clearly you can see that B is not equal to C. So if A intersection B is equal to A intersection C, this does not necessarily imply that B also has to be equal to C. Similarly, if A union B is equal to A union C, again this does not necessarily mean that B has to be equal to C. And again you can see this example here, it's slightly modified. Let's suppose our set A is 1, 2 and 3, B is 2, 4, C is the element 4. So here A union B is 1, 2, 3 and 4, which is the same as A union C, but here also B is not equal to C. So these are little pointers that you should know. I will now introduce to you all the idea of a universal set, and also related to that, the idea of the complement of a set. Let us suppose you have a family of sets, then we can think of the universal set as a set that every set in the family that we are thinking about belongs to. So every set in the family, if it is a subset of a particular set which we can think of as a universe, that constitutes the universal set. To understand this, let's use an example. Let us suppose we want to examine the characteristics of a particular set of employees in a company called Com. And in particular, we are interested in the employees who are married and also the employees who have a college degree. They are college graduates. And here we have data on the employment for 2017 for this company Comp. And on the basis of this, let's suppose we define the set A. If you look at the slide here, the set A is defined as a set of all workers who are married, and the set B is a set of all workers who have a college degree, they're college graduates. In this context, we can think of a universal set as the set of all employees that have been hired by Comp in the year 2017. So we have to think of some universe which is relevant to a story, and a universe within which these sets A and B can be accommodated. In other words, A and B are subsets of this particular universal set. As an aside, let us also do our set operations with these two sets. So if set A is a set of all workers who are married and B is a set of all workers who are college graduates, then A union B would be the set of all workers who are married or who have a college degree. Please note the use of the word or. So here we'll have workers who are married and don't have a college degree, workers who are married and at the same time have a college degree, and also workers who are not married but have a college degree. We can also talk about the intersection of A and B, which would then consist of all the workers who are both married and have a college degree. And then finally, A minus B would be the set of those employees who are married but do not have a college degree. Now, related to this, let us introduce the idea of a complement, or the complement of a set. Let's define, let's suppose we represent our universal set by the symbol omega. This is a symbol called omega if you look at the slide. And let us suppose we have a set A which is a subset of the universal set omega. Then the complement of this set A is represented in terms of notation by, if you follow the movement of my cursor, the complement is represented by A with an upper bar or A with the superscript C, and it represents the set of all elements that are a part of the universal set omega but not a part of A. So everything outside A but in the universal set. And mathematically, the complement of A is nothing but omega minus A. And in terms of the Venn diagram, where A was our set of all workers who are married, so A complement would be everything outside this orange circle, but within the rectangle which represents our universe, represented by omega. Now let's work our way through some examples using Venn diagrams. And let's suppose our question is verify the following formula using Venn diagrams. The formula here is the union of A and B intersection C is equal to A union B intersection A union C. This is also known as De Morgan's. This is actually one of De Morgan's laws. And diagrammatically, if we look at the left hand side, the Venn diagram would be drawn as follows. So B intersection C, if you look at the slide, is the blue shaded region between, which is the overlap between B and C. And you take the union of that with the set A. So this entire shaded region, which consists of the set A and the blue shaded region below A, that constitutes our left hand side. And now all we have to do is to check that the right hand side formula also gives us the same shaded region. The right hand side region is the intersection of A union B and A union C. Now what is A union B? A union B, if you look at the slide, is the entire shaded area in blue here, which spans A and B. And A union C is the entire shaded region in red. So wherever you see the red and the blue lines together, which is again, you see this is corresponding to the set A, along with this little overlap between B and C below the set A, and that is then the verification for our formula which constitutes De Morgan's law. Our second formula states that A minus B union C is equal to A minus B intersection A minus C, and you can do this yourself. You can check for yourselves that A minus the union of B and C is this shaded area. So the union of B and C would be this the entire area on B and C, which is blank here, and if I remove this area from A, so then I'll get this blue shaded area, which is A minus B union C, and you can verify that the right hand side is also the same. We will now do a formula for A union B, which is actually very important, and you please pay attention here. Suppose A and B are arbitrary finite sets, then you have to prove that the number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. To see this, we can draw a Venn diagram showing the union of A and B. Now, this is the entire span for the sets A and B that represents a union. Now, we can divide this into three mutually exclusive regions. If you see here, we have divided A union B into this orange region, which is just A, just the set A. Then we have the overlap, which is the black region, and then we have the red region. In particular, the orange region, which is to the left of A intersection B, is nothing but A minus B. The overlap, if we've already introduced, is A intersection B, and the red region, the red shaded region, is B minus A. So, because these are mutually exclusive sets, that makes our life easier, which means that the number of elements in A union B would simply be the sum of the elements in all these three sets taken separately. So, the number of elements in A union B is the number of elements in A minus B plus the number of elements in A intersection B plus the number of elements in B minus A. Now, as I pointed out earlier, A minus B is nothing but A minus A intersection B. So, the number of elements in A minus B can be written as the number of elements in A minus the number of elements in A intersection B, and then our middle element is number of elements in A intersection B. Then finally, similarly, we can write number of elements in B minus A as the number of elements in B minus the number of elements in A intersection B. So, if you look at these expressions here in the second last line, the second and the third terms will get cancelled, and you'll be left with your formula, which says that the number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. And this is a very important formula. We can actually extend this formula to see how it will work for three sets. So, let's look at the number of elements in A union B union C and show that it's equal to this expression on the right hand side. To simplify our life, let's assume that the set A union B is given by the set D. So, if we look at the number of elements, instead of writing A union B, now I have D. So, the number of elements in D union C by the formula that we just established, that is equal to the number of elements in D plus the number of elements in C minus the number of elements in D intersection C. Now, let's replace A union B for D to come back to our original sets. So, now n of D is n of A union B, then the second term is n of C, and in the third term we now introduce our A union B back instead of D. So, we get minus n of A union B intersection C. Then in the third step, I have simply expanded on the first term. So, n of A union B is n of A plus n of B minus n of A intersection B. Then my next term is n of C, and then finally I have my last term. And actually the last term, we can use De Morgan's law, which is a distributive property, and in the last line you can say see that I can write A union B intersection C as A intersection C union B intersection C. So, with this as the expression, let's continue. We have reached to the point where we've written the number of elements in A union B union C as the number of elements in A plus the number of elements in B plus the number of elements in C minus n of A intersection B minus n of A intersection C union B intersection C, and this is where we left on the previous slide. Right. So, how would we expand on this? note here that the last expression here in the first, where my cursor is, this is also the union of two sets. So in the next step, what I can do is I can again I can again substitute for my union union of two sets formula. So I'll have in my second step, instead of A intersection C union B intersection C, I'll have A intersection C plus B intersection C, the number of elements in A intersection C plus the number of elements in B intersection C minus the intersection of A intersection C and B intersection C. So this in turn gives me, in fact, if you notice, now I'm in a position where I have all the terms ready for my final expression which I was supposed to prove, except that this last term here, if you follow my cursor, needs a little bit of manipulation. Now let's see what our intersection of A intersection C and B intersection C amounts to. So we can see this through a Venn diagram. If I want to look at the intersection of A intersection C and B intersection C, now A intersection C is this common overlap between A and C, and the area B intersection C would be the red overlap between B and C. And the intersection of these intersections is this little area which is common to all the three to all our three sets, and this then is our A intersection B intersection C. So we have now finally proven that number of elements in A union B union C is equal to number of elements in A plus number of elements in B plus number of elements in C minus n of A intersection B minus n of A intersection C minus n of B intersection C plus n of A intersection B intersection C. So this is a little difficult to elaborate, but that's how it is. Anyway, so let's do one more example, and then we will call it a day as far as our examples are concerned. So here we have a situation where we have 100 paying guest rooms in our Delhi University campus area, and a survey of that revealed that 38 rooms had refrigerators, 52 rooms had TVs, and 21 rooms had both a TV and a refrigerator. So the question here is how many rooms have a TV but no refrigerator, and there are other questions also, but let's get our work started. Let's first bring our data together and write it down in a systematic way using set notation. Here, if you notice, our universal set has 100 elements. We're talking of 100 rooms in all. So the number of elements in omega, which we call our universal set, is 100. Let us represent by the set R the set of rooms that have a refrigerator, and let us represent by the set T the set of rooms that have a TV. So as per the question, the number of elements in R is 38, the number of elements in T is 52, and the intersection between R and T would have 21 elements. Let's put all this down in a Venn diagram because that will make our life much easier. So here our intersection is 21 elements. Then the number of elements in R is given as 38. So this means that if we just consider R without the overlap, then the number of elements in just R would be 38 minus 21, which is 17. And similarly, the number of elements in just T would be 52 minus 21, which is 31, which is written here. Now, suppose my question is, what is the number of rooms that have a TV but no refrigerator? That would be now given by T minus R, because I don't want the elements that I don't want to look at those rooms where there is a refrigerator as well. So we will look at T minus R, which is nothing but 31. Similarly, if I want to look at the rooms that have a TV or a refrigerator but not both, then I'm looking at the regions where we just have R or just T, but we're not looking at the intersection. So that would be 17 plus 31, which is 48. And finally, if I ask you what is the number of rooms that have neither a TV nor a refrigerator, that would be the number of elements in the universal set, which is 100. So we have 100 rooms in all, and from that you subtract off the number of elements in R union T. So because R union T represents all those rooms that have a TV or a refrigerator or both. So 100 minus 17 plus 21 plus 31, which is 69. So 100 minus 69 is 31. Right. So I will not do this example as we are running out of time, but before I end, I will introduce this very important concept of what is known as the symmetric difference between two sets A and B. The symmetric difference between two arbitrary sets A and B is denoted in terms of a triangle, and it is represented as A minus B union B minus A. So let us see how this looks on the Venn diagram. A minus B would be just the region represented in A without the overlap. So this is the green region to the left of A intersection B, and B minus A is the green region to the right of A intersection B. So A symmetric difference B is this union, which is this entire green region in the two sets. And you can see here that this is nothing but A union B minus A intersection B. So A union B would be the entire area spanning the two sets, and from that you just simply subtract off this white area, which is the A intersection B area, and that would give you the symmetric difference. Intuitively, symmetric difference is nothing but the regions that correspond to just A or just B. Now let us see what this means for three sets. So if I were to look at the symmetric difference of three sets, which is A symmetric difference B, symmetric difference C, that consists of all those elements that occur in just A or just B or just C or else in all three. And this is something you can do as an exercise. So just A would be this blue region here, where my cursor is pointing. Just B would be this region, and just C would be this bottom region of C. And the region consisting of all three sets would be this middle region of overlap. And this then corresponds to the symmetric difference between three sets. And with this, I come to the end of this discussion on set theory. The next session, in the next lecture, I will talk about functions, a little bit about functions, and I'll also introduce some formulas from coordinate geometry. But until then, goodbye.
Thank you, Dr. Bhutani. We thank you all for joining us for this session. We hope that you have got a great insight into set theory, and all the examples which are being discussed by Dr. Bhutani have given you a very practical point of view or insight into how you are going to solve the problems of set theory. Friends, if you have any suggestions or questions regarding this session, you can mail us on to our mail ID, which is info.cec@nic.in. And thank you for joining us, and we thank you again, Dr. Bhutani.
Thank you, Disha.